Now here comes the trickiest part of the solution. We choose a point H in the line segment AB with the length of AH equal to 1/2. Recall that the length of AB is m, which is greater or equal to 1, so it is possible to make this choice. Now let lines A and H be perpendicular to AB and passing through A and H respectively. And let P be the strip between A and H, including the boundary A and H. Now we consider the intersection of P with the set of endpoints S. We set T, script T, to be equal to P intersection S. Namely, there are the points in S contained in the strip P. Now let T be the cardinality of script T. So this set T consists of the points of S lying in this purple region. And in this picture, there are 3 points in T. Little t is equal to 3 in this picture. And this yellow strip is the region where we're going to find the contradiction with the proper choice of delta, or the constant c. And now we focus on this line segment AH, whose length is 1/2. Which will give an estimate for this t. And the fact that this A is a point in P intersection S. Here we are using that P contains its lower boundary. We know the line segment AH contains at least this many points of SL. 1/2 divided by 2 delta seeding points of SL. I hope this is not hard for us to see. Any 2 adjacent points have distance less than 2 delta. And you just count how many points are there. Because their distance is small enough, so there will be at least how many points? It should be 1/2 divided by 2 delta, and you want to take a seeding. Noticing that A is in here. But note that T is the cardinality of the script T, the intersection of S and P. And the points in T will project onto the line segment AH. So the number of points in T will be greater or equal to this quantity. Considering that there are cases where 2 points might project onto the same point on this line segment AH. So T must be greater or equal to this quantity, which is, let's simplify it. This is greater or equal to 1/4 delta. And we'll denote this inequality as equation number 2. Just in case you got confused about this inequality, let me add a comment. And this is due to the fact that T, which is the definition, P intersection S, and remember S is contained in dB. So T is really contained in the strip intersection dB, which is this purple area. That is the basis of this inequality here. Okay, now let's move on. Let us look at the intersection of H with this circle, the boundary of dB. Suppose H intersects the boundary of dB at points H1 and H2. So this is H1 here, this is H2. Then we can give a length estimate for H1 and H2. The length of the line segment H1, H2 is equal to 2 times the square root of m squared minus m minus 1/2 squared. So this is just by the Pythagorean theorem. Remember, this AH is of length 1/2. So BH is of length m minus 1/2. So the line segment H1H can be computed through the Pythagorean theorem in this right triangle, because the radius BH1 is m, and the length of H1, H2 is twice of this. This is very easy for you to see. And this is equal to m minus 1/4 square root twice. And we only need to use this estimate later. We bound this by 2 times m square root. Okay, so on the one hand, we have an estimate for the line segment H1, H2 here. On the other hand, if we consider the projection of those points onto the line segment H1, H2, we'll get a surprise. You will find that there might be too many points on the line segment H1, H2. And somehow there will be a contradiction. And now we are going to find this contradiction. For any 2 points, xy in T, which is P intersection S, we have their distance is greater or equal to 1 by the assumption of this problem. And if you look at the projection of those points onto AH, if you look at x sub L and y sub L's distance, this is less than or equal to 1/2. Since XL, YL live in AH, AH length is precisely 1/2. So, if we now project x and y onto the line H, if you look at the line segment XH, YH length, by using the Pythagorean theorem again, this is greater or equal to root of 3 divided by 2. Okay, well, the length of the line segment H1, H2 has an upper bound. The distance between any 2 points coming from the projection of T onto H1, H2, this distance on the line segment H1, H2 has a lower bound, root of 3 divided by 2. And you might expect a contradiction starting from here. Now consider T sub H, the projection of T onto H, the line H. Now since the length of line segment XH, YH is greater or equal to root of 3 divided by 2 for any 2 different points xy in T. No 2 points in T could be projected to the same point in H in particular. And as a matter of fact, there will be at least root of 3 divided by 2 apart. This tells us the cardinality of TH will be same as the cardinality of T. Which is, by our notation, equal to T. And now we summarize this. To summarize, the T points constituting script T sub H will lie on the segment H1, H2 with the length of H1, H2 less than 2 times root of m, and those t points are at least root of 3 divided by 2 apart from each other. And this yields two times root of m greater than t minus 1 times root of 3 divided by 2. Or, in other words, we move t to one side, the t is less than 1 plus 4 times root of m divided by 3. And we can majorize this to 4 times root of m. Here we are using the fact that m is greater or equal to 1. And 4 times 1 minus 1 over root of 3 is greater or equal to 1. I will denote this inequality by 3. And now we are ready to combine our inequalities 1, 2, and 3. Now combining 1, 2, and 3 is, so first from 3 you get t less than 4 times root of m. This is by 3. And by 2, you get t greater or equal to 1 over 4 times delta. And by 1, you know 4 times root of m is less than 4 times 2n delta. And look at the head and the tail. They will give us this inequality. 1 less than 16 times root of 2n delta times delta. Now you simplify this. This is 1 less than 256 times 2n delta times delta squared, which is equal to 512 times n delta cube. But remember, delta is c times n raised to the power negative 1 over 3. This is 512 times c cube. So we can conclude our contradiction. So if we take c equal to 1/8, then we get a contradiction. Because 8 here raised to the power 3 is precisely 512. That gives a contradiction to this inequality. If you don't feel safe, you can even take c to be even smaller to contradict this inequality. But 1/8 is good enough. So with this contradiction, we can finish the proof, because this contradiction origins from our assumption here. Suppose it is not the case that there's a line with blah, 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 blah. So the only case that could happen is this first case, which is the desired situation of this problem. So we have proved the existence of such a line. So we are done.